Hello everyone, this is the first introductory video for Toolkait. Toolkait is a free online tool with no installation required, no coding knowledge needed, and it allows you to easily create, train, test and explore your own neural networks. You can use your own data or data freely found online. Toolkait isn't intended to compete with major platforms or large neural networks like ChatGPT or others, but rather to help people understand how they work, how to train neural networks, how to create language models or generate images. With Toolkait you can create networks that perform classification, for example using data from a spreadsheet like Excel. You can perform regression, generate images, generate text, and create all sorts of neural networks, very simple networks or more complex ones like autoencoders, variational autoencoders, transformers, diffusion models, and so on. There will still be small networks. You won't be able to do anything huge, but you will be able to do many different things and above all explore, practice and understand how it works. So in this first video I'm going to explain the basic concepts necessary to understand and get started with Toolkait. First you need to understand what a neural network is and how it works. So if you already know what a neural network is, how it works, and if you are comfortable with the concepts of layers, activation functions, loss function, tensors, and so on, you don't need to watch this video. You can skip to the next one, which will explain in more details how Toolkait works. If you are a complete beginner with neural networks, watch this video first to get an understanding of the main concepts without getting bogged down in overly complex mathematical considerations. First, a few clarification on the terminology. We are talking about neural networks, which are also known as deep learning, a subset of machine learning, which itself is a subset of artificial intelligence. With neural networks and deep learning, the idea is to teach machines how to learn, drawing inspiration from the neurons that exist in our brains. So we create neural networks that aren't the same as biological neurons, but are inspired by them to enable machines, computers, to learn in a way that's similar to how our brains can learn. So it's not the same thing, but it's inspired by them. So what is at the heart of the neural networks? It's the neuron itself. An artificial neuron inspired by natural neurons, but not exactly the same. And what exactly is an artificial neuron? It's really nothing more than a tiny, very simple calculator. So its operations are incredibly simple. The neuron is what's represented by a circle in this image. It has inputs, several inputs. Here there are 3 of them, but there can be hundreds or thousands, and only one output. Only one output for each neuron. Each input is associated with what's called a weight, that is a multiplier. We multiply the input of each neuron by a number. So here you see we have, for example, 0.3 minus 0.2, 0.5. These are all multipliers. And you can see that we have also a threshold. The threshold is set to 1, but it could be something else. This is really a very simplified example. So in our neuron there are inputs. Information that comes in here is represented by these values at the bottom. So you have 1, 1 and 0. So for each input there is a number. It will simply be multiplied by the multiplier and the whole thing will be added together. So for example, in our example we have 1, 1 and 0. So we have 1 times 0.3 plus 1 times minus 0.2 plus 0 times 0.8, and the whole thing is added together and we get 0.1. This is less than the threshold, that is 1. So the neuron returns 0. This is a very simplified example of a neuron, and you can see that all it does is really like a very simple little calculator. It performs multiplications, it performs additions, and it compares the result to a threshold. If the value is below the threshold, it returns nothing. If it is above the threshold, it returns 1. Indeed, you see in this second example, if we change the inputs, instead of 1, 1, 0, we have 1, 0, 1, and we do perform the calculation. So we have 1 times 0.3 plus 1 times minus 0.2 plus 1 times 0.8, and we get 1.1. So this time we are above the threshold, and the neuron returns 1. Now my example is a bit simplified because, as you can see in this scenario, the neuron returns nothing, and if the value is above a certain threshold, then it returns 1. This is this case. In practice, we have what we are called activation functions. So once the neuron has added the inputs, it can return different values, like what you see here. You have many different functions, but I won't go into these details here. The goal is simply to understand the general operations. So you might ask, how do we create intelligence with all this? How do we manage to create intelligence with this tiny neuron, which is essentially just a little calculator? And how can we have machines capable of imitating human thought? Well, these neurons work in layers. They are never alone. They are assembled in layers within what we call a neural network or a model. Here is a very simple example with 4 layers. In a model like this, we always have an input layer, that is the first layer, and an output layer, that is the last layer. And in the middle, we have intermediate layers called hidden layers. So in a large model, that can be several hundreds layers like this, or sometimes in small models there are just 2 or 3 layers. And within each layer there are several neurons. Here we have the same numbers of neurons in each layer, but it can be different numbers. And there can be several thousands or several hundred thousands of neurons in each layer. And these neurons are interconnected. So again, it varies depending on the type of layer. Here we are considering the case where all the neurons are connected. All the neurons in a layer are connected to all the neurons on the previous layer and on the next layer. So how do we use these neural networks to do something resembling intelligence? Let's take an example, a very simple case of what we call classification. We want to train a neural network to recognize images, and when presented with a photo, for example, capable to identify what it is. Is it a horse? Is it a dog? Is it running? Is it eating? And so on. So I'm going to give you a very simplified explanation of how it works. So for that we need to train our neural network, and we need a very large number, several hundreds of thousands of images, for which we know whether it's a horse, a dog, whether it's running, whether it's eating, and so on. We need to have these informations already, and we are going to use these informations to train our neural network. So the first step is going to be to transform our image. As you can see, it's actually made of pixels. To simplify things, we will consider that these pixels can be either white or black. So black is 0 and white is 1. Obviously, in reality, images have many more pixels than that, and they also have different values, not just 0 or 1, and several colors. So it's an oversimplification in order to understand better. So we are going to match each of the neurons in our first layer to a pixel in our image. I can't show them all here because I've only included 4 neurons, but in practice, for this exercise, we have 8 pixels this way and 10 pixels in this direction, so it makes 80 pixels. Therefore, we would need 80 neurons on our first layer. And then on the last layer, we'll have our different categories: dog, horse, run, eat, and so on. So we can have as many neurons on our last layer as we have categories into which we want to classify our images. So we put the values of each of our pixels in the first layers, and then, as I explained, each neuron behaves like a little calculator. Each of the inputs we see here, represented by an arrow, is associated with a multiplier, as we saw in the first images. So it will multiply the value of the neuron in the first layer by these multipliers. If we are below the threshold, it will be 0. If we are above the threshold, it will be 1. So this is what we call forward propagation. From the input layer, we go to the second layer. When then the same thing happens, we go to the third layer, and finally we arrive at the output layer, where each neuron will have a value of either 1 or 0, depending on the multiplier coefficient we used. At the beginning, it's completely random. The multiplier coefficients, the weights we assign to each input of each neuron, are completely random. So for the first images we feed into the neural network, the result is random. Here, sometimes it will find the right match, but that's a chance. Other times, most of the time, it will be wrong. So how do we train our neural network? This is where it gets really interesting. Each of our neurons can adjust its weight to get closer to the correct value. For example, let's take the case of a neuron that predicted 0. Let's say it's the neuron in the output layer that corresponded to horse. This neuron here. Since it was an image of a horse, it should have returned 1, but it returned 0. So there is an error, because the inputs multiplied by the weights all added together equal 0.1, which is below the threshold of 1. So it returned 0. Now let's look at this and see if we had slightly increased this weight, this multiplier, and slightly decreased that one, the error would have been less significant. If we recalculate, let's say we replace 0.3 with 0.4 and minus 0.2 with 0.1, here we redo the calculation and we find 0.3. We are still below the threshold, so the neuron still returns 0, but the error, the difference between what I find and the output that will have given the correct answer, is slightly less significant. Therefore, this correction worked, modifying the weights of the multipliers associated with each neuron. We will do it for all the inputs for the entire output layer. So we do the same thing of correcting the weights for all our neurons of the output layers. Some will get higher, some will get less. And we will correct this and then work our way back from the output to the input. This is called gradient descent and backward propagation. And we are going to slightly adjust all the weights, all the multipliers of each neuron, so that the output for this example, the running horse, will be a little less inaccurate, a little closer to reality than it was initially. And we are going to do this not just for a few images, but for hundreds, thousands, sometimes hundreds of thousands or millions of images. We will repeat this process. We will train it. Each time we will send the information into the neural network. It will calculate an output that will be generally inaccurate, and will slightly modify all the multipliers, all the weights of each neurons, so that the error is a little less significant. And you might think that the adjustment will sometimes increase, sometimes decrease, and that all these weight changes will cancel each other out. But it's just the opposite that happens. With large numbers of examples, gradually we see that what's called convergence, and little by little the error decreases and the neural network becomes increasingly capable of accurately predicting the outcome. This is called generalization. That is to say, at a certain point, not only is it able to accurately predict the outcome of the images given to it as examples, but if it's given new images with which it hasn't been trained, it will also be able to predict correctly. This is a bit of the magic of neural networks, the way we manage to train these tiny neurons, which are essentially little calculators, and gradually decrease the multiplier coefficients, the input weights of the neurons, so that the prediction error becomes lower and lower, lower and lower, until we arrive at a neural network that is truly capable of very accurately predicting what we want. So if we go back to this concept of error, as I mentioned at the beginning, an untrained neural network receives inputs and produces output that will generally be completely wrong. That's what we call error. We also call it a loss, the loss of a neural network. That's the difference between what is predicted by the model and what was expected. And as we train the model, what we want to do is reduce this loss. So how does it work? Well, there are algorithms called gradient descent algorithms, as we said just before. And to visualize this without resorting to overly complicated mathematical concept, imagine a mountain. The loss is like a mountain, except that the mountain is actually incredibly complex and exists in thousands of dimensions. Each weight of each neuron represents a dimension of this mountain. It's hard to truly picture, but it works roughly the same way as a real mountain. The higher up the mountain you are, the larger the loss, and the lower down the mountain you are, the smaller the loss, and the closer you get to what you want, to the right answer. The whole point of the neural network is to descend the mountain, and to do this, it generally just follows the steepest slope. So imagine we start at the top of the mountain and look around. Each time we don't have a clear idea of the mountain's shape. We don't know how to get down. But each time we look at where we are and see where the slope descends fastest. And we try to take the path. And generally it works well, and we manage to descend, thus minimizing our loss and our mistake. But sometimes it doesn't always go so smoothly. Sometimes we fall into what's called a local minimum. That is, in a mountain, you should imagine it as a basin. If we descend, and then at some point we find ourselves stuck in a kind of hole. All around us the slope rises, but we haven't actually descended to the bottom of the mountain. So this is what happens, what can happen quite often with a neural network, is that you train it, and then after a while it can no longer improve because it's stuck in a local minimum. So for that we use algorithms called optimizers. And the optimizer is the algorithm that tries basically to get down the mountain as quickly as possible while avoiding getting stuck. So what do we do when we see that the error is no longer decreasing, that the loss is no longer diminishing? We try to get out of the local minimums, the pit of the mountain, so that's what we call the optimizer. There is another concept that's often important, which is what we call the learning weight. I told you that for each example we use to train a neural network, we correct, slightly decrease or increase the weights, the multiplier coefficients of each neuron. Well, we can do this with varying degrees. These are always small modifications. We won't change them drastically, but we can achieve a very high learning rate. So in this case, imagine we are going down the mountain, taking big steps. We will go very fast, but sometimes we won't find the small path. Whereas if we take smaller steps, we might descend much more slowly, but it will be more likely to find the shortcut, the small path that leads to the bottom of the mountain. So this learning rate is one of the parameters of our neural network, of our learning process. We will try a higher or lower learning rate, and we won't necessarily get exactly the same result. Another important concept you will need to use if you are using Toolkait is the notion of batch. In the example I gave you, we processed image one by one. The first image, then the second, then the third, and so on. In reality, when we work with neural networks, it's not like that. The examples are grouped into batches. Here, in what I'm showing you, they are grouped in threes. There are 3 images each time. In practice, it's often much more. You can have batches of 60, 100, or even 200 examples at a time. The learning process will be much faster because the computer, the neural network, is capable of processing multiple images simultaneously. Another concept is the notion of epoch. This means that each batch of images isn't presented to the neural network just once. Instead, it's repeated many times, resulting in several epochs. So, for example, I train my networks with batch 1, then with batch 2, then with batch 3. That is the end of the first epoch, and so on. In reality, there are many more batches, and then when that's finished, when I've processed all my images, I start again from the beginning. And that's my second epoch. Batch 1, batch 2, batch 3, and then epoch 3, 4, 5, and so on in the same. Sometimes there can be 500 or 1000 epochs depending on the neural networks we want to train. So batches and epochs are very important concepts. When you train a neural network, you will see this kind of curve appear. This is the learning curve. As I was saying, our goal is for the curve to go down as far as possible. So imagine this is our loss mountain, and we want to get it as low as possible. So on this axis, you have what we call the loss or prediction error of the neural network. And here are the epochs I was talking about. That is the number of times we have trained our networks with all of our training data. And you see that there are 2 curves, because when we train our neural networks, we always keep a portion of the images. We always keep a portion that we call validation data to see if our model is learning correctly. In blue here you have the training data. So these are the images that are actually presented to the neural network, allowing it to adjust its weights. And in orange, that's the validation curve. We keep a small portion, often 10, 15 or 20% of the data. We don't use this to train the neural network, we just use it to check the result. And sometimes we realize that the two curves diverge. This is what we call overfitting, and it's not good. In other words, if at one point your network is very good at predicting the data you are using to train it, but it has some difficulty predicting data you haven't used, it is generalizing poorly. That is to say, it can only predict the example it was given to train, but it struggles to predict other data that wasn't given as an input. So when training our neural network, we need to try to ensure that these two curves don't diverge too much and there is no overfitting. So the example I use is what we call a classification example. That is, we give an image to a neural network and it will try to classify it into categories like dog, horse, and so on. It works roughly in the same way for generative networks. Even if there are differences, they are not exactly the same network, as we will see in the future videos. There are many differences, but the basic principle is the same. For example, image generation. Instead of giving the network an image and then wanting to retrieve categories, we give the network categories, for example dog, horse, run, eat, and then it will generate an image. It works broadly in the same way, even if there are significant differences. We won't necessarily use the same layers in the same way. It's not exactly the same, but the basic principle is the same. The same applies to text generation, like with ChatGPT. We'll give our neural network words as input, the words of a sentence, and he has to predict the next word. That's how a text generator works. We provide it with the words at the beginning of the sentence, and it finds the most likely words that can follow. So again, there are many specificities. It doesn't work exactly in the same way, but the basic principle is the same as we saw in the first example. There is one last thing to cover in the concepts that are important to master before really getting into using Toolkait: the notion of tensors and TensorFlow. So what are tensors? It sounds complicated, but actually the principle is quite simple. All the data we have, whether it's images, text, everything contained with our network, that is the weights, inputs, outputs, losses, error, and so on, all of this is represented by what we call tensors. So what are tensors? Basically, they are very simple. They are simply arrays of number. They are arrays of number. Now you have one-dimensional tensor, which we call vectors. See, here you have a vector of 5 elements, so that's a one-dimensional tensor. Two-dimensional tensor are called matrices, so they have rows and columns, and you can have 3-dimensional, 4-dimensional, and 5-dimensional tensors. We can't really visualize them. For 3 dimensions, you have to imagine a cube with each cell of the cube containing a value. But 4-dimensional and 5-dimensional tensors are too complex to visualize, but mathematically they work in exactly the same way. So why is this different tensor with different dimensions? For example, a one-dimensional tensor, a vector, corresponds to the weights of a neuron. All the weights of a single neuron are represented as a one-dimensional vector or tensor. Or if we are speaking of data, if you have, for example, an Excel spreadsheet and you want to predict a person's debt risk based on their age, gender, income, and country of residence, it will take the form of a one-dimensional array containing only numbers. There is no text, no symbols, nothing at all. Everything is converted into numbers. So that's a one-dimensional tensor or vector. A two-dimensional tensor or matrix will be, for example, in a neural network, the set of weight for an entire layer of neurons. So on one axis you have the different neurons in the layer, and on the other axis all the weights of each neuron. Or if it is data, you can have tables, a batch, again using our example, the Excel spreadsheet of several people. There you go, you have 3 people. It really looks like an Excel spreadsheet with the information corresponding to several people. A three-dimensional tensor is used very often for images. So why 3 dimensions? Because you have both the height and width of the image, but you need a third dimension to encode the color. So if you have a black and white image in grayscale, it will be a single number ranging from 0 for absolute black to 1 for white, and all the values in between will be shades of gray. But when it's in color, we have 3 numbers. So it's still a 3-dimensional tensor, but in the last dimension there will be 3 values, 1 for red, 1 for green, and 1 for blue. The same thing will range from 0 to 1. And then you have 4-dimensional tensor, that for example a batch of images. That is to say, when you process several images at once, it will be a 4-dimensional tensor. So the first dimension will be the number of images we have, the second dimension is the height, the third dimension is the width, and the fourth dimension is the color. And then we can potentially have 5 or 6-dimensional tensors when we want to process, for example, video or things like that. So why do we talk about tensors like this? It's actually about the calculation technique, so I won't go into detail, but know that all these elements are optimized to be calculated on our computers, and in particular on our computers' graphic cards that we call GPUs, which are capable of performing very complex calculations all at the same time. So to give you only one example, you will see that the operation of a neural network requires an enormous amount of computations. Let's take the example of this very small neural network with 3 neurons on the first layer and 5 neurons on the second. To calculate the output of each of my 5 neurons, I need to take the value of the 3 neurons and multiply it by the associated multiplier coefficients, the weights. So it is represented in the form of a table like this, which are tensors as I mentioned. Here is a 2-dimensional tensor, a matrix, which are the weights of each neurons of the second layer. And here is a 1-dimensional tensor, a vector, which represents the output of each of the neurons of the first layer. So to calculate the output of the first neuron of the second layer, we have to multiply the value of that neuron by the coefficient, the weight. So we have to multiply the output of this neuron of the first layer by the weight of the first weight of the first neuron of the second layer, and the output of the second neuron by the second weight, and the output of this neuron by this weight. So you see, and then we have to add all this together. So just to calculate that, just the output of one neuron, we have 3 multiplications and 2 additions to find the result. And we have to do that for each neuron in the entire network. Here I've only included 5, but obviously in real networks there are thousands, millions, and then we'll have to repeat it for each of our images. So you see, each time it's just small calculations, it's not much, but that plus that plus that adds up to millions and millions and millions of calculations that are very complex and very time consuming, even for very powerful processors. So we use GPUs, the graphic cards in computers, which have circuits designed to perform all these calculations all at once. This is where we save a huge amount of time. Instead of performing each calculation and multiplication one after the other, graphic cards can multiply this tensor by each other, add them together, and perform many operations between the tensor very quickly, because they do all the calculations simultaneously. And so obviously it's much faster for training our neural networks. So as you'll see in Toolkait, when we move on to the practical application, all the data we use must always be converted into tensors, these kinds of arrays of numbers, so that we can feed them to our neural network to work. That concludes this very general overview of what a neural network is. Now in the next video I'm going to show you more specifically how this is implemented in Toolkait and where and how to find all this information in the different Toolkait screens. See you soon!